Good morning, everybody, and welcome to today's Antech Controls by Price webinar on laboratory exhaust devices. Today's webinar is accredited for one professional development hour. After the event, everybody who's attended the live webinar will receive an email with a link to request a PDH credit for this. You can submit questions any time during today's presentation using the chat or question function on your toolbar. We will get to those questions at the end of the presentation as time permits. There are no costs or cancellation fees associated with today's webinar. Today, what we'll be presenting on are laboratory exhaust devices. So this webinar is aimed at helping engineers understand and apply the most common equipment found inside the laboratory. These are fume hoods, biological safety cabinets, and snorkels. And what we'd like to talk about are control strategies for each type and really how each type of device differs from the other. Each one is used in different applications to do different things inside a lab, and so each one can and should be controlled a little bit differently. At the end of today's webinar, you should likely be able to describe the most common types of fume hoods. You should also be able to identify the difference between a constant volume and different types of variable volume fume hoods. We should also be able to select the correct type of phase velocity control based on the type of fume hood we're selecting. Further, we should be able to identify the class and type of a given biological safety cabinet, and we should be able to select the correct control strategy for the application of a laboratory snorkel. Each of these topics we're going to dive into a little bit here today. My name is David Enns. I'm a professional engineer with a Bachelor's of Science in Mechanical Engineering, and I'm the Business Development Specialist for Antech Controls by Price. I've been with Price Industries for about 6 or 7 years here now. Today's agenda, what I'd like to go through with you guys today is about a half an hour on fume hoods, about 15 minutes on biological safety cabinets. Sometimes some of them are called glove boxes as well. We'll talk for about 10 minutes about snorkels, and hopefully we'll have about 5 to 10 minutes for questions right at the end. Before we get into this, however, before we start actually talking about the equipment, we should talk about the standards where we pull most of this information from. Each of these is a very, very good reference for laboratories and has very clear descriptors on the equipment in the lab. So ANSI Z9.5 and the 2019 ASHRAE Handbook on HVAC Applications are extremely good references for laboratories. If you'd like to know more than what we talk about here today about fume hoods and bio cabinets, these are great references. If you're looking for more information on how to test or work with a fume hood, the ASHRAE 110 standard is a very good reference. And similar to that is the NEB Fume Hood Performance Testing Standard. So those last two, number 110 and the NEB standard, those are specific to fume hoods, not to snorkels or biological safety cabinets. Today we'll start with likely the most popular piece of equipment in a laboratory. Fume hoods are really what we talk about most in the laboratory controls business. Every lab is unique. Every lab has different types of equipment, different types of users. They're used to mix and match different types of chemicals. But really one of the unifying themes in a laboratory is that most of them have fume hoods. Most teaching and research spaces will have fume hoods, or at least certain laboratories in a building will have fume hoods for these researchers. So this is really what we want to spend the most time on here today. Fume hoods come in a lot of shapes and sizes and a lot of different types. You can have small 3 or 4 foot hoods. You can have up to 10 foot or 12 foot wide walk-in fume hoods for certain applications. The ASHRAE Handbook breaks these down into several different categories. I've bolded the ones we'd like to talk about most today. That's constant volume and variable volume. We'll also talk a little bit about low velocity or reduced flow hoods. We're going to talk about floor mounted hoods as well, just a little bit, and we'll spend some time on perchloric acid hoods as well. There are a few other types, as you can see. We won't spend any time on auxiliary air hoods or filtered or recirculating hoods. We won't talk about radioisotope hoods, California distillation process, or canopy hoods as well. Those exist, they are usable, they do have an application in this world, but the ones we bolded here are really the most common types we're going to deal with. We're going to start by putting constant volume and variable volume fume hoods side by side. Constant volume fume hoods were previously a little bit more popular when energy was a little bit cheaper and we didn't have to worry about lowering our air change rates in laboratories. However, constant volume fume hoods are still quite popular. They're still in heavy usage today, but they do have a certain application we're going to touch on. Constant volume fume hoods are sometimes called open bypass hoods. The reason is they have a bypass that will open progressively as the sash opens or closes. Meaning as we open up face area, we will close off the bypass, meaning that a constant or an approximately constant volume of air will hopefully provide us a not too variable face velocity on that fume hood. Now, if you actually look at the ANSI Z9.5 standard, it does state specifically that they use an approximately constant volume with a variable face velocity. But really the intent is that they provide relatively stable face velocity, so likely in the range of 80 to 100 feet per minute. However, as you close that sash down on a constant volume fume hood, the fume hood may go as high as 3 times that face velocity when it's opening and closing there. So these aren't as precise of a control device, but they are perfectly acceptable in laboratories. They are in full usage today in certain laboratories. This is a good cut of a constant volume fume hood. So on the left, you can see the louvered front panel at the top of the fume hood. That would be one example or one type of constant volume fume hood bypass. So as that sash, that red line there, as it opens, that bypass will proportionally close, meaning, let's say a set 500 CFM will always have a pathway through the fume hood to allow it to exhaust at a constant set rate. Now, there's a couple things I want to touch on here for constant volume fume hoods. That same ANSI Z9.5 standard basically requires that we always monitor fume hoods. So whether it's from the fume hood manufacturer or the valve and controls manufacturer, there needs to be a local display of face velocity. There needs to essentially be something to tell a user or a researcher it's okay to use this fume hood, it's operating normally. So whether that comes on the hood or it's installed later, we do need to include that for these constant volume fume hoods. A lot of times that will look very similar to the controls, however, they are just monitors for face velocity. Now you might ask the question, when should I use a constant volume fume hood? And to explain that, I'd like to use a bit of an example. So consider a laboratory that has a ventilation airflow of 1,000 CFM. That's our minimum air change rate is at 1,000 CFM. We can't go below that. This laboratory is to be negative, so it'll have about, let's say, 1,100 CFM of exhaust from somewhere. This lab is to have one constant volume fume hood in it. That fume hood's about 4 feet wide. It opens to 12 or 18 inches, so it needs, 500 or 600 CFM of exhaust air when the sash is open. Well, that 500 or 600 CFM is well below the 1,000 or 1,100 we need on exhaust. So whether it goes through the fume hood or a general exhaust type of valve, that air must be exhausted. This application, where the constant volume fume hood won't inflate our makeup air numbers, that's a great application of the constant volume fume hood. The really great thing about a constant volume hood is they come with much more simple controls. They're easier to apply than a VAV hood. There's less movement in the VAV system or a true constant volume system. This makes it easier to design that ductwork system and fan system. So that's a great application for a constant volume fume hood. But not all laboratories are designed this way. In some cases, we'll design a laboratory that will be fume hood driven, meaning say we have 4 or 5 fume hoods in that same laboratory. When each of them opens to 500 CFM, we would be required to exhaust 2,000 CFM out of that lab. But our minimum ventilation airflow rates might still be 1,000. What this will do will inflate our makeup air numbers. Reducing makeup air or, not introducing more makeup air is one of the quickest ways to create a more efficient lab. Makeup air is what costs money. It's what costs energy in a laboratory. So if we're allowed to turn these fume hoods down, meaning as we require less air to maintain face velocity, we can turn down that exhaust airflow rate, meaning we can turn down our makeup airflow rate. So variable volume fume hoods certainly do have a place in this world. In our experience, these would be the most common type of fume hood going into laboratories today. Not as a legacy product, but going in today, this would be your most common type of fume hood. So these hoods, variable volume or restricted bypass hoods, are defined that as the sash opens, the air volume required to maintain face velocity must be increased. Meaning as you open up more open area, you need more airflow to maintain a certain selected face velocity. These may still have some sort of small bypass, meaning when you close the fume hood all the way down, you might have an airfoil with a gap underneath it. You might have a sash that doesn't actually close all the way down. You may have openings on the left and right-hand side of the fume hood to allow some air to pass through. We're not going all the way down to 0 CFM when we close a fume hood. We'll go down to some minimum flow rate. We'll talk about what that number can be in a little bit here. But variable volume fume hoods are a great way to conserve makeup air, as we mentioned. So these should be used in more fume hood dense laboratories. There's not really a definition or a clear-cut definition of a dense fume hood laboratory. Our general rule of thumb is if you can save that makeup air, however, you should likely look at a VAV hood. It will save you money in the long run, even if it's just a few CFM per year. 1 CFM of makeup air, depending on your market and your design and your equipment, it can cost you anywhere from $3 to $10 per CFM per year. So if you can save a few CFM of makeup air on any hood, there's a long-term savings to be had there. Those would likely be the most common types. Constant volume or variable volume, they look fairly similar. They're employed in the same types of spaces as far as application goes, maybe not as far as density and size goes, but those are likely the most common types. Inside the constant volume and variable volume type, you might also see reduced flow or low velocity hoods. A lot of VAV hoods can work at a range of face velocities, and we'll talk about what that means shortly. But some of them might not need to operate at, say, 100 feet per minute. They can operate down to 80 or 60 or maybe even 50 feet per minute. We would still class those as part of the VAV type hood. The same would go for floor mounted or walk-in fume hoods. These are really just bigger, different style VAV hoods, or maybe even constant volume hoods. We won't spend too much time on those today. However, one thing we'd like to talk about here now that's more of a unique product is the perchloric acid hood. Perchloric acid is its own separate entity. It's not like hydrochloric or sulfuric or bromic acid, more common types of things we'd see in a laboratory. Perchloric acid gets its own special place in all of these guides and standards. And it's not so much about the hood, it's not so much about the valve, it's about the acid itself. Perchloric acid is an extremely active oxidizing agent. It's used in a lot of different chemical reactions. And what can happen is when perchloric acid dries, essentially, the vapors can form an unstable deposit in the ductwork. It forms what's called perchlorate. Perchlorate is extremely explosive. So unfortunately, in the past, there have been instances where perchlorate has exploded, it has harmed humans, it has unfortunately killed people in the past. So perchloric, like I said, gets this separate part in all these standards to describe how we need to build these systems. And what the standards state are these last 3 points. Hoods, ducts, fans, and stacks should be equipped with water washdown capabilities. Ductwork must be smooth and seamless, and these cannot be part of a manifolded system. It's those last 2 points that are extremely important to us today. They must be smooth and seamless, and they can't be part of a manifolded system. We'll start on the last point. Anytime you have a perchloric hood, it must be on its own dedicated system with its own dedicated fan. If you go to the letter of the standard here, if you have 2 perchloric hoods, they must each be on their own manifolded system, their own fan. So if you have 2 side by side, that's 2 separate systems. The second last point there is also what causes a bit of concern or a bit of a problem here. Ductwork must be smooth and seamless. So you can see on the right-hand side of the slide here, we show a Kynar-coated Venturi valve. There's a bit of an issue here. The Kynar coating and Teflon coatings on Venturi valves can technically survive a perchloric acid environment. The coating will stand up to that acid. So you might actually see a check mark beside a lookup chart that says Kynar is good with perchloric. The valve here isn't actually the concern. If you look inside that valve, or if you look at either end of that valve where we would mount it into the ductwork, they're filled with seams. They are not smooth, they are not seamless. So while the valve could technically work in this operation, we cannot apply a VAV or constant volume Venturi valve or high accuracy terminal. We cannot apply those in a perchloric acid system. These are essentially constant volume systems that go directly from the perchloric hood to a fan. Those fans will be designed with a bypass, so that perchloric is never actually introduced to the fan system and never has a place for that perchlorate to form where it can't be washed down with water. So what you're seeing on the slide here is a bit of an issue. Remember, we have to have a seamless system. We cannot use the valve we show on the slide. You cannot use a Kynar coated valve, even though the valve itself would technically be okay. So we're going to keep going here, not so much with the fume hood types, but with the different types of control to apply to those fume hood types. So when we're looking at constant volume, or more importantly, variable volume, they come in a few different types here. They come in vertical, horizontal, and combination style sashes. The most common will likely be the vertical sash on the left-hand side there. A vertical sash is a single pane of glass that only moves vertically, up and down. So the width of this hood, the width of that opening, is completely set. This is the most common, the most simple style. In the middle, you see the horizontal style. These exist, they are well applied sometimes. They're just not as common as a vertical sash. Combination sashes are becoming more popular. They're a little bit more costly, but they do have a few more uses inside the laboratory. They're a little bit easier to work with, and those horizontally moving panes of glass can provide you a bit of a shield as a user in front of them. So sometimes we will see the combination sash applied. Each of these three different fume hoods will require a different type of control. Let's look first at a vertical sash hood. The most common way to control a vertical sash fume hood is using a sash position sensor. You can see that device at the top of the screen there. It's just a simple stainless steel drawband that pulls itself in and out and basically tracks the movement of a sash. Remember, with a vertical sash, the width of it is set. It might be a set 35 inches wide, for example, but the height can change. So what we can do with this system is we know the width, and now because we have a sash sensor, we can measure the height of that sash. If we take the width multiplied by the height, we now know an open area. We've also previously likely set a face velocity we'd like to maintain. We would have selected about 100 feet per minute. So if you know an open area and you know a velocity you must maintain through that open area, it's an extremely quick and an extremely simple calculation to figure out how much flow you need, to figure out the volume of flow you need. So if you know you have 10 square feet of open area and you'd like to maintain 100 feet per minute, well, that's about 1,000 CFM you'll be required to flow through that opening. So this is an extremely quick system. However, sash position sensing is what's known as an open loop control strategy. This isn't actually measuring face velocity. This is assuming a face velocity. It knows an opening size, and it knows what flow it's currently at, so it can calculate what face velocity you're at. If you stand in front of this fume hood, or if you reduce or open up that open area somehow, the fume hood won't control for that difference because it hasn't seen the face velocity actually change. So this is a very quick strategy, but it is an open loop strategy. It is still the most popular style of control. What we show here are two different ways you can mount that sash sensor as well. On the left is likely the cleanest option. This is going to be mounted to the counterweight in the back of the fume hood. If an installer has access to the hood, this is the best way to install it. It's clean, it's unseen by the user, and it's out of the way so nobody can play with it like a guitar string or cut it with a pair of scissors. If that's not accessible or not possible, on the right-hand side, you can see that sash sensor could also be mounted right inside the fume hood as well. The only downside to this is it's visible to the users of the lab. And again, you may not know who's actually using the lab. It could be a teaching lab for first-year college or university students. They might see something and try to pull on or play with that string. So ideally, we just keep it out of their field of vision. That works very well for a vertical sash hood. And again, that is the most popular type. When you're looking at a horizontal sash hood, there are a few different options. There's actually two main options you have to control a horizontal sash. We show one of them here today. I'll start with the other one, however. You can apply that same sash position sensing theory to a horizontal sash hood. What you can do is measure how much open area there is, basically with overlapping magnetic strips connected to those horizontally moving sashes. This can be a quick and effective way to control a sash. However, it still doesn't deal with that issue of somebody coming and standing in front of the fume hood, taking that open area and reducing it just with their presence, just with the fact that the human body takes up some space. So that is one method. Another method you might see as well is an actual measurement of face velocity. This is sometimes called sidewall sensing. A sidewall sensor is actually a pressure sensor. Fume hoods are generally designed to maintain a relatively constant pressure differential between the laboratory and the inside of the hood. You can measure that pressure and relate it to face velocity. So while you might call this face velocity measurement, it's actually a pressure measurement. This is a truly closed loop style of control. It doesn't matter what CFM you're at. It doesn't matter what introduced a change in open area. This system will just measure the face velocity and control for it. So if you have low face velocity, provide more air. If you have high face velocity, provide less air. It's a fairly simple closed loop strategy that will just actually feed back that information. This won't be as quick as a sash position sensing system. However, depending how you define speed of response, it still can typically meet those speed of response requirements you may have. This type of system, a sidewall sensor type of system, is also an extremely effective monitor. If you're looking at a constant volume fume hood, you can use this not as a control mechanism. You can use this purely as a monitoring system. So measure that face velocity and relay it back out to the user of the fume hood. Doesn't have to control anything, it can just display that information. So this is where you can start to get creative with your control strategies. If you'd like that quick speed of response, if you'd like that open loop control of a sash position sensor, you can use that for control of the hood. But you can now also employ a sidewall sensor to monitor that face velocity. Not for control, but just for monitoring. So now you get a bit more dynamic of a system. It's quick, it's very, very speedy, but it's also giving you an accurate readout of that flow. You can also get a little bit more creative even, and you can actually combine these two strategies into a very effective two-stage control system. So what I'm getting at is if you have a combination sash, combining these two styles of control into a hybrid style is extremely effective. A combination sash may still be operated as a vertical sash. That might be moved up and down vertically. In that case, you do want that quick speed of response from a sash position sensor. However, if that sash is closed and the horizontal panes of glass are moved and opened and closed, that sash sensor won't be very effective. Actually, it won't be effective at all. That's where a sidewall sensor can be used. So what you can do with these control strategies is stage them. Essentially what you can say is while the sash is in motion, only the sash position sensor is in control. As soon as the sash stops moving, give control to the sidewall sensor. So now these two pieces of equipment can work in concert and provide an extremely dynamic, fast, and accurate system. So for a combination sash, that would be our recommendation, is combine these two styles into one control strategy. So I mentioned earlier, we would come back to talking about fume hoods in the closed position. Sometimes we get the question of, it's fairly easy to calculate what flow we need in the open position, but what do we do at closed? Some campuses will have a set standard. They'll provide, 1/3 of the opening position's flow at the minimum flow. Others will try to target a face velocity of 100 feet per minute at closed. ANSI Z9.5 gives us a fairly clear-cut range of flows. What ANSI Z9.5 states is you require between 150 and 375 hood air changes per hour. That has been shown to provide containment in the closed position. So if you'd like to lean closer to the bottom end of that, at about 150 hood air changes per hour, on a 3 or 4 or 5 foot hood on a smaller fume hood, you can get down to 70 or 80 CFM in the minimum position. At the open position, say you open to 18 inches, that same hood might require 500 CFM. So again, this is where on a VAV hood, there can be a huge savings when going from 500 CFM down to 80 or 100 CFM. You can save 400 CFM of exhaust air, meaning we save 400 CFM of makeup air whenever the fume hood is closed. The safest fume hood in the world is a closed fume hood. No matter what fume hood type or style or what occupant is using it, an open fume hood is less safe than a closed one. It's a simple fact of fume hoods. So these should be closed for most of their life, meaning when we're using a VAV system and VAV hoods, hopefully we're in this more energy efficient mode much more often than we're actually using the fume hood. So that's where the VAV hood and calculating this minimum bypass flow are extremely important. Now, we've talked about different types of fume hoods, different applications for them. We talked about control strategies for them, but really all we've talked about are control strategies for face velocity. Now, unfortunately, face velocity isn't the be-all and end-all of fume hood containment. It's actually, on its own, it's an inadequate indicator of fume hood performance. It is the easiest one to see, it's the easiest one to measure, it's the easiest one to control for, but face velocity alone is inadequate as an indicator of fume hood performance. That being said, again, most of what we talk about will be about fume hood face velocity. Sometimes we'll get the question about what face velocity should I use. This is typically provided by the fume hood manufacturer. Sometimes they'll say you need 80 to 100. Some will say you can go down to 50 or 60. If you don't know, a generally accepted number is about 100 feet per minute. That being said, again, that is just an estimate. That's just a general rule of thumb we use. If you have a specific reason to go with a different face velocity, that's perfectly acceptable. But the real answer for a fume hood, what is the right face velocity? The right face velocity is whatever will provide containment for the hood is right. Meaning, as long as we pass a tracer gas test, a face velocity test, and a flow visualization test, it doesn't matter what you pick. So a proper fume hood containment test will include 3 parts. It's not one individual part, it's all 3 of these. You can do tracer gas testing, you can do flow visualization testing, basically using smoke pens or smoke generators to basically watch where the flow goes, or you can do face velocity testing. When we're doing tracer gas testing, this is just defined in great detail in ASHRAE 110. However, while that standard breaks down how you should release the gas, where you should release it, how you should collect data, how often, it describes every part of this test extremely well. What it will not tell you, and it's very straightforward about this, is it will not tell you what the correct amount of containment is. That is for the facility staff, operational health and safety. It's for the facility and the design engineers to determine for themselves. Nobody will give you a straight answer about what the right number is. That's up to you and your application to define. The same will go for flow visualization testing. Whether it's a huge release of smoke inside the hood or just a small smoke pen along the sill, it's up to those groups to determine what an acceptable criteria is. When you're looking at flow viz testing, essentially you're trying to avoid lazy airflow, meaning if we release a gas inside the hood, it should generally trend always towards the back of the hood, towards the back of that baffle where it can be exhausted. If it performs as reverse flow, it's sometimes called, meaning it moves towards the front of the hood, that is lazy airflow. That's not what we want to see. There should be a general momentum, a general trend towards the back of the fume hood. Face velocity testing, as we mentioned, is the third part of this. This is defined fairly well in 3 different standards, unfortunately, and each standard is a bit different. We're going to talk about two of them here today, and that's ANSI V9.5 and the ASHRAE 110 method. There is also the NEB fume hood method, and we'll touch on that very, very briefly. ANSI V9.5 from 2012 has a very clear definition of fume hood response, or VAV response of a fume hood. Sometimes this will be called speed of response. The VAV response shall be sufficient to increase or decrease flow within 90% of the target's flow or face velocity in a manner that does not increase potential for escape. The next section, however, is the most important part. A response time of less than 3 seconds after completion of the sash movement is considered acceptable. Faster response times may improve containment. There's a few words here that are extremely important because they vary between the standards. So the great thing about Z9.5 is it states you have 3 seconds or less, but it also states when to start your stopwatch. So as soon as that sash stops moving, that's when you start your stopwatch. If you have a data logger or if you're watching or measuring the face velocity, you have 3 seconds or less to get within 90% of your required face velocity or flow rate. So it's a very clear-cut, simple definition. Pardon me. ASHRAE 110 is similar, but has some gray areas. ASHRAE 110 provides a little bit more information, however, that's very, very useful. It states that you should open the sash from the closed to design opening at a rate of approximately 1.5 feet per second. In previous versions of this standard, that was 1 to 1.5 feet per second. It's clear cut now and states 1.5 feet per second. So if you have an 18-inch opening, it should take you 1 second to open that fume hood. A nice, clear cut and defined number for how we should open this. However, its definition of speed of response is a bit different. It states this is the time measured from the first movement of the sash for the VAV system to restore the slot velocity to 90% of its flow. Now remember, we have a method for measuring how quick to open the sash, but we also have to start our stopwatch at the beginning of sash movement. So take that ANSI Z9.5 number and add 1 second to it. That's essentially what an ASHRAE 110 test will show. But ASHRAE 110 doesn't actually give us a number. It doesn't say you have 3 seconds or less. It doesn't say 10 seconds or 1 second. It says it's up to you. Those groups we mentioned earlier, the groups responsible for the operation of the fume hood, it's their job to determine what an acceptable criteria is. A lot of groups use the 3 seconds from ANSI Z9.5 and apply it to this standard. However, there's no clear-cut definition in the standard of that. The NEB standard is very similar to ASHRAE 110 in that it states a rate of sash movement. It also doesn't state an actual speed you have to maintain. However, it's a little more gray on what it actually shows. It states to start your stopwatch after a change in sash position. Well, we know the change takes about 1.5 seconds or 1 second or so. So do we start the stopwatch at the beginning, the middle, or the end of the change? That's not clearly defined in this standard. As I understand it, this will be updated in the future to more align with one of the two standards, whether it's Z9.5 or ASHRAE 110, to clear up this gray area here. So the important thing to remember here is, regardless of the type of control you use, regardless of the type of the hood, there's 3 ways that we have to measure containment. That's face velocity testing, flow visualization, and tracer gas testing, all for containment. If we're looking specifically at face velocity, we have a few clear-cut guidelines, or fairly clear-cut guidelines on how to actually measure that. But it's the combination of all 3 that provides a good measure of a working hood. I just wanted to touch on a couple accessories at the end here before we move to bio cabinets, just as a part of the control of a hood. Some facilities will like to use presence sensors. If you have poor sash management, meaning a researcher uses a fume hood and then walks away from it and leaves it open all night, a presence sensor can be one effective device to save you some energy. Meaning, instead of 100 feet per minute, it might be safely operated at 60 feet per minute. We can use a presence sensor to set that fume hood control back. However, this is only effective when the sash is open. If you have good sash management, if people close these hoods, you don't need presence sensors. In a similar vein are automatic sash closers. These are a mechanical system that will close the sash when, after a certain timer expires, they notice nothing in the way, they'll close the sash down. These are extremely effective because the most efficient fume hood is a closed one. And forget about efficiency, actually. The safest fume hood is a closed one. As we understand it, in California, Title 24 is going to be updated, and these will become mandatory in certain types of laboratories. They define it as fume hood dense laboratories, basically measuring the linear feet of fume hood you have and comparing it to the volume or air change rate in that space. Some of those may become mandatory. Next, I'd like to move on to biological safety cabinets. These are sometimes common in laboratories. They're less common than fume hoods, I would say, but they are very common in pharmacies. So we call this laboratory exhaust devices, but there is some crossover to compounding pharmacies. Biological safety cabinets, abbreviated as BSCs, are broken into 3 classes: Class 1, 2, and 3. Class 2 is actually further broken down into 4 subcategories that we will dig into. I want to make a statement here, and I'll make it at the beginning and I'm going to make it at the end. Biological safety cabinets are not fume hoods. I state this because as a manufacturer of valves and controls for laboratories, we make specific controls, as you saw, for fume hoods, for control of a movable sash. Biological safety cabinets generally do not use those controls. Regardless of if you're talking about Antec or not, most manufacturers work in a similar style. Fume hood controls are dedicated to fume hoods. BSCs are not fume hoods. Let's get into Class 1 hoods, however. Class 1 is what you might call a lower containment type of hood. That definition of low versus high containment isn't broken out in the ASHRAE handbooks or the standards. They just state it's a lower style of containment. However, one of the defining features of a Class 1 cabinet is it's suitable only for protection of the worker. Just like a fume hood, it's suitable only for protecting the person using it. The reason we say that is unfiltered, unconditioned air from the lab is pulled directly across the agent being mixed. There's no filtration whatsoever. So all of that air is pulled in and 100% of it is exhausted. So this looks like a fume hood, I understand that. The real defining feature, however, is these typically have an 8-inch fixed opening. Fume hoods have a variable opening. That's the key difference here. So you'll see these in some non-hazardous, non-toxic spaces to mix up certain drugs or chemicals. But now we need to move into Class 2. But remember, Class 2 is broken into 4 subclasses, or 4 types. Those types are A1, A2, B1, and B2. Type A1, or actually all Class 2 devices, are suitable for protecting the agent being mixed and the person and the environment, meaning these protect everyone. So there's filtration everywhere on these devices. The clear definer between the A types and the B types is that second point. Types A1 and A2 include an internal fan. There's something to boost your pressure so it's not required to be made up by your exhaust system. So these have a fairly low static pressure requirement, in the range of 1/10 of an inch, give or take. The internal fan will overcome the filter pressure requirements. So in the A types, most of the air will be recirculated inside that hood. So there's less demand on the actual exhaust system. 70% of that air for a type A1 will be recirculated. The other 30% will be exhausted. That air that's being recirculated will be filtered through a HEPA and washed over the product. To define between A1 and A2, we get the last point. These generally have an inward air velocity of about 75 feet per minute. Type A2 is extremely similar. It includes an internal fan. It can protect the agent being mixed, the person, and the environment. It's got a low static pressure requirement, and 70% of air is recirculated. However, the inward air velocity is a bit higher. So you might consider this a slightly higher type of containment. A lot of compounding pharmacies that are going in for the updates to USP 800. If you'd like more on the update to that standard, we do have an engineering webinar previously done on that as well. This is generally the cabinet we're seeing go in there. This is a good image, or good couple images on how these actually look. So you can see room air is pulled in through those blue arrows. It's filtered down through a fan, and it either exhausts through a HEPA or is pulled down through a HEPA to actually wash over the agent being mixed. So you can see how it protects the environment, the worker, and the agent being mixed all at once, all while maintaining a fairly low pressure drop on your system. Class 2 is still, or sorry, type B1 and B2 are still inside the Class 2. Similarly, they're good for protecting the agent being mixed, the person mixing it, and the environment. They'll do all the same things, but the defining feature here is there's no internal fan. So what you'll notice on the third point on each of these slides is they have a much, much higher static pressure requirement. For type B1, it's in the range of 0.6 to 1.2 inches. So your exhaust fan must overcome this filter pressure. As those filters load, your exhaust fan has to deal with that as well. In the type B1, only 40% of air is recirculated. Most air is pulled over and exhausted out to protect the person. So these are, again, a slightly higher type of containment. Air is still internally HEPA filtered before it's exhausted or washed over the agent. So that's very similar to the A types. Inward air is, again, about 100 feet per minute. B2 is very similar, but 100% of air is exhausted through HEPA filters. These have an extremely high static pressure requirement. We have seen these also applied in pharmacies, typically in the range of about 1.5 to 2.3 inches of pressure is required to overcome those filters. This is a fairly big draw on your exhaust system to overcome these pressures. If you're working in a retrofit and your pharmacist or your researcher has requested the type B2, you may need to look at your fans. Even if you were planning to keep them, you need to check to see if your fans can handle the load required by a B1 or a B2 cabinet. Much less of a concern with an A1 or A2 type cabinet. Again, here's a similar but good cut of the B types, the B1 and B2. So you can see no fan there, just a way to recirculate that air, but all that HEPA filter pressurization requirement is done by the rooftop fan. The last is Class 3. So this isn't split into subcategories. These are sometimes called glove boxes. So at the beginning, we talked about bio cabinets and glove boxes. You can see very clearly on the right why we might call these a glove box. A Class 3 cabinet physically separates you from the agent being mixed. It's not just inflow of air. There's glass between you. There are the gloves between you and the agent being mixed. So if you're looking at a high containment, a BSL 2, 3, or 4 lab, it's some version of this style cabinet that physically separates you from the worker. That's your Class 3 type of hood. It is the highest containment in the biological safety cabinets. So now let's talk about biological safety cabinet control. You can see I lean on this point quite a bit. This comes up a lot in the control of laboratories. Biological safety cabinets are not fume hoods. They do not use fume hood controls. They don't use sash or sidewall sensors at all. Generally, they're actually operated as constant volume devices. They need to exhaust that 30% or 60% of air that's required at all times, 24 hours a day, 7 days a week. So that can be done by a constant volume system. Some of them require full shutoff of that system for decontamination or isolation of the filters. You may want to do that with a separate bubble tight damper, for example, or you might want to do it at the airflow control valve, which we'll talk about more in a second. One important thing to remember on a biological safety cabinet is the filters. The filters will load over time. So while we're trying to provide a constant flow, some mechanism needs to be provided to overcome that changing static pressure drop in the system. It's more important for a Class B1 or B2 cabinet where your exhaust fan has to do this. Really, it should be the high accuracy terminal or the Venturi valve we use to overcome those changes in pressure. So what do we recommend you actually use here? You've got quite a few options. We show 2 of them here. Ideally, we would actually use a constant volume Venturi valve. That would be our #1 recommendation. Regardless of the accuracy or the pressure drop, this is the simplest way to control it. A constant volume Venturi valve, like you see on the left there, has no electronics, there's no nothing. All there may be is a pressure switch, meaning it's a low pressure switch, meaning if pressure is present, the airflow we need is present. So that's all the feedback we need. It's the most cost-effective, easiest to apply solution there is amongst all of these options. We could also use a high accuracy terminal or even a VAV box. However, the way we measure flow in those might lead you away from that. High accuracy terminals can work. There's a couple points we'd like to make, however. Number one, they require a controller. You must control this style of VAV box or high accuracy terminal, so the cost will be inflated over that of a Venturi valve. And you should use standard speed actuators. They don't need to be high speed. You're controlling to a constant volume, so introducing a high speed actuator is only introducing instability and a more tough control strategy. So please use standard speed actuators here. Your third option would be just to connect the bio cabinet directly to likely a dedicated fan. That can work. However, it might be a little tougher to control. It might be a little more complicated on the fan side. Introducing an airflow control valve can keep it actually a little bit more simple. So now we've covered fume hoods, which are likely the most popular. We've covered biological safety cabinets for laboratories and talked a bit about them in compounding pharmacies. We'd like to spend a bit of time here now on snorkels. There's not a lot to say about snorkels. They're a product we apply fairly regularly. I actually often present that snorkels are what can make a lab unique, because if you have one snorkel or 15, you get a very, very different lab, even if all other things are held equal. Snorkels are often, as well, misunderstood. Snorkels, according to ASHRAE, according to the ASHRAE handbook, should be used to remove heat and non-toxic particles generated in benchtop applications. They don't generally exhaust highly toxic chemicals. So again, these are not fume hoods, these are not biological safety cabinets. These are not high containment devices. So first and foremost, you don't need a coating on whatever air valve you need. This can likely be an aluminum valve because there's nothing here that's going to eat away at the airflow control valve. But how do we actually control these? How do we use them? Regardless of the snorkel type, regardless of the manufacturer, you have a few options. Combining the options is what makes snorkels a topic of conversation. Generally, snorkels are either two-position or constant volume. The most simple option, bar none, is constant volume. My recommendation is snorkels should be included in your general exhaust system. They should be hooked up past your general exhaust valve. We should control the volume of air through them. So if you have one snorkel, you might want one airflow control valve that just holds it at a set constant volume. It never turns off. There's no wasted airflow here because the 100 CFM we provide through the snorkel, for example, is just removed from the general exhaust system. It's constant volume, so there's no dynamic between the two. It's an extremely simple system. The other option, generally, is a two-position style of control. Two-position is a perfectly acceptable way to control a snorkel, but it introduces complexity, which is okay. It just needs to be dealt with in design. The reason it introduces complexity is the two-position is unclear. Where is that two-position provided is the real question we have to ask. You can see the image on the right. There's a selector, there's a manual damper on the snorkel. So if we provide a set constant volume through that snorkel, the user can turn it on or off. They can 100% shut it off or 100% open it up. That's a simple way to do it. You could also remove that manual damper or order the snorkel without it. Then you could put a push button on the wall to control two positions on an airflow control valve, whether it's a VAV box or high accuracy terminal or Venturi valve. All are options. But that could control the actual valve itself. The key here is don't do both at the same time. Don't give users the manual damper and the push button, because then you get multiple different logic states that some will be at a minimum position, some at a close. Two positions could be actually maximum on the snorkel. You introduce too much complexity and it's just not required for a snorkel. Generally, again, we want to keep these as constant volume styles of valves. The question comes up, how should we actually control the airflow here? You've decided on how to operate the snorkel itself, whether you pick constant volume or two position. We decided how the users will use it. But what will we actually do to control that airflow? As I mentioned, constant volume Venturi valves are the simplest, same as a biological safety cabinet. There's no electronics required other than a low pressure switch. There's no actuator, no controller, no logic built in, just a low pressure switch to allow us to monitor that airflow. Sometimes when we get large numbers of snorkels, so you can see that in the image on the right again, if you get 3, 4, or even 5, 6, or 12 snorkels, you may want to bank them together into manifolds. This will come up mostly in teaching laboratories. A lot of times these teaching laboratories are turned off for the night. They're only used for 3 to 6 hours a week or something like that. We may want to switch those snorkels off. We may also want to deal with smaller class sizes that might come and go as the years pass. So what a good method here is to take those 12 snorkels, for example, and put them onto 3 or 4 different manifolds, and then provide a 2-position Venturi valve to switch each of those manifolds. So you can turn on 3 or 4 snorkels at a time, but once they're on, they're constant volume. There's no manual damper, no nothing like that, but you can turn on those banks. This would essentially be up to the instructor to know how many people will use them and turn on the appropriate snorkels at any given time. So again, snorkels can introduce a lot of variability to a lab, pardon me. They can introduce a lot of complexity if we'd like as well. Our recommendation is to keep snorkels simple. They are a simple device. They exhaust heat and non-toxic particles. So using them as a simple device is the best way to go. We only have a few minutes left here, so I'd like to talk briefly about room controls. How do we integrate this into the lab at large? Some of you may have seen this before, but there's generally 2 theories on how to control room pressure. Labs are typically negative spaces, so how do we control that negative pressure? The most common way in a laboratory is airflow offset control, which you might also call volumetric control or volumetric offset or tracking control. Those are all the same thing. And what this does is, regardless of what happens in the laboratory, we maintain a constant CFM offset between all of our supply and all of our exhaust, completely independently of room pressure. This is a very, very simple strategy, and it's by far the most common solution. The other option is pressure control, where you completely ignore that CFM offset. We know we will use an offset, but we don't care what it is. All we do is control to an actual pressure set point by controlling one of the valves or some of the valves in the space to actually hit that -0.01 or -0.02, for example. Pressure control works. It's a perfectly viable strategy. It's just less common because, again, it's a little bit more variable and it introduces a little bit more complexity. However, we mentioned some BSL labs might require it. It might be just a facility requires it, and that's perfectly okay. So the last point we'll make here before we open this up to questions is that in room controls, fume hoods are high-speed devices. They use high-speed actuation. When you open that sash, the control system needs to respond quickly. So use high-speed actuators. This will not make a flow offset control strategy any more complicated. It's just as easy at high speed as it is at standard speed. Where possible, use constant volume valves on snorkels and biological cabinets. If you can, or if you want to, I should say, move into a 2-position control, this can help you reduce air change rates on some of the devices, but it introduces a bit more complexity. It's a little bit more complex than CV, but it is much more simple than VAV. So those would be our recommendations in this laboratory. So with that, we'd like to thank you all for your time. We have a few questions here, but I'll give you about 15 or 20 seconds to ask a few more questions before we get into them. After the fact, if you did register and attend, we will be sending out a quiz automatically after the presentation here. Once you complete that quiz, your PDH credit will be issued. In the future, if you have questions, please email applications@antechcontrols.com and we would be happy to assist you. So we'll start with the first question here. The question was asked, does ANSI require 150 to 370 air changes or CFM when the sash is closed? Just to clarify that, ANSI Z9.5 requires 150 to 375 fume hood air changes per hour. So take the volume of the fume hood, say it's 4 feet wide, they're often 2 feet deep and about 4 feet tall on the inside. That volume must exchange 150 to 370 times per hour. Question was asked about perchloric acid hoods. Do all electrical parts need to be explosion-proof as a standard and fan spark resistant? To my knowledge, yes, they do, which just further lends itself to keeping the system simple, putting it on a dedicated fan, and not including any sort of airflow control device in there. All of that stacks up and basically precludes the use of those valves. Another question asked here are what are the pros and cons between room controls versus the CFM offset versus pressure controls? The pro for offset control is simplicity and stability. It's independent of room pressure. So whether pressure is actually maintained or not, the system is stable. So it's easy to set up, it's easy to balance, and then it's very, very stable for the life of the product. The pro for pressure control is its accuracy. Whether you open or close fume hoods, introduce cracks or leaks or things like that, it will control to an actual pressure. The con to that is that's not as stable. You will see movement in your system. So the question was asked here about snorkels. How do you maintain airflow through each snorkel? The total airflow can be maintained at the valve, but as the snorkel position changes, the pressure changes through each individual snorkel. So what's important here is to only give control to one spot. If you're using a constant volume valve, you should not provide users with switches or manual dampers at the snorkel. So for example, you have 4 snorkels on a single constant volume valve exhausting 400 CFM. If each user has a manual damper at their snorkel, when the first user closes their damper, the other 3 snorkels will now flow 400 CFM total. Close another damper. Those 2 snorkels are now still exhausting 400 CFM. Go a step farther, and 1 snorkel will then try to flow 400 CFM, if the system can even handle that. The worst case scenario is we do that, and then we close that last snorkel, and if we don't have a pressure switch to monitor that flow, we have no idea what that pressure or what that flow is. So in this example, if you're using a constant volume valve or 2 position valves to manifold them together, don't provide them the ability to shut their snorkel off. They should be manually balanced against each other, just with a simple manual damper to a set CFM. So the last question we'll have time here for is, can you explain why it's recommended to use a standard speed actuator instead of a high-speed actuator for a pharmacy project? A lot of times we like to go to high-speed actuators because the thought is that high speed is better and higher containment. It's a better device than standard speed. We have to look at the application, however. So to back up, for a fume hood, high speed is better. High speed is the right example to use there. So inside the laboratory, as soon as you have fume hoods, you should use high-speed actuators everywhere. In a pharmacy, these are constant volume applications. So you'll be at that 30 air changes per hour all day, all night, 24 hours a day. There's no change required. That biological safety cabinet is the same way. It might need to exhaust 500 CFM at all times. So ideally, there's actually no movement required from the valve serving that hood, meaning whether you're high speed or standard speed, it shouldn't be moving. In reality, for the small amount of movement that will be required, it doesn't need to be quick. There are minor changes in duct static pressure typically that can be taken up very, very effectively by a standard speed actuator. We're not making broad, sweeping, large changes. So a standard speed actuator will be just fast enough to do that, and it's more cost effective and more simple. High speed actuators move quicker. With any control loop, as you introduce more speed, you introduce the possibility for instability. That's about all the time we have for questions here today. If you have any, again, after the fact, please reach out to us at applications@antechcontrols.com. Thank you all for your time and have a great day.